All right. Hello, everyone. This is the Advanced FEA Workshop hosted by Rob. You may have seen him last night in the alumni panel. So without further ado, let's get underway.
Okay. So again, for the purposes of the recording, I don't have an educational background in FEA. I never took any classes when I was at UCLA. My knowledge is based on experience in industry. So there are probably going to be some things that I may get wrong. That said, this is going to cover kind of the basics of how SolidWorks works under the hood and things that you probably need to be aware of when you're creating models in order to get meaningful results. The topics to be discussed today include meshing rules, and I guess there was a question about whether I should go over contact problems, and someone else was interested in design studies. And the good news is that all of those are kind of related. So they're easy to go over in a single discussion. So I'll start right away with meshing rules. These are probably one of the more important and more basic functions within SolidWorks. So I have here this fictional bracket that I've created here, and I'm going to go into SolidWorks, and I'm going to go into my SolidWorks add-ins tab, and I'm going to enable SolidWorks Simulation. And if any of this seems a little bit more basic than what you guys want to go over, if you guys already know this, just tell me and I can skip ahead. So we'll go into SolidWorks Simulation, and that'll enable the Simulation tab over here. And you get a bunch of options. One of them is New Study, or you get the Simulation Advisor. I have no use for Simulation Advisor. I just click New Study. And there's a number of different models that you can create here. I'm on my work computer, and so I've got access to everything. We pay for the premium license. You, on an educational license, probably are only going to be able to access the static simulations. But that's fine. That's what we're going to use today. So we'll pick static. We'll just call this static 1. Leave that unchecked. Hit just OK. So now we're in the model creation, or the model creation window. And this is the name of our study, is static 1. This list here is going to be a list of all the solid bodies, or solid and or surface bodies that are in your model. In this case, I'm only simulating on a single part, so there's only one part. And if this part has a material assigned to it, it'll say right next to it. So we're going to right click on this, and we're going to apply or edit material. You can also apply a favorite material, so all of these. So we'll pick apply material, and we'll go through the list. And we can really pick just anything. It doesn't really matter. All the model is going to care about for now is Young's modulus and Poisson's ratio, or elastic modulus as it says here. And one thing worth noting is that all of the elastic moduluses for the steels are basically the same. Here, 4340, 2 to the 2 e to the 11th Newton meter squared, 4340 annealed, 2 e to the 11th Newton meter squared, 4130, 2 e to the 11th Newton meter squared, 1020, 2 e to the 11th Newton meter squared. What that means is that if you're simulating a material that like say you're going to make in the context of a combat robot, say you're going to make a weapon out of some super fancy chromoly alloy that you can't get material data for. It's perfectly fine to simulate with any other grade of steel, or pretty much any other grade of carbon steel, because the elastic modulus is going to be the same. Pretty much all steels have the same modulus, or within a couple percent. All aluminums have the same modulus within a couple percent. Doesn't really matter. So you don't need to kill yourself trying to find material properties. Just pick one. I'll just pick 1020. Okay, so now you can see that the material is called out for this model. We don't need to do anything about connections because this is a single part. It has no connections to other parts. We can add some fixtures. I'm going to fix the bottom two pads of this bracket as if it was bolted to something. Notice I have bolt holes here. We're going to use those later. And then we can create some loads. So we just create a force. Say the force acts here. Now, when you select a force on a surface, it's going to create that force evenly distributed all across the whole surface. And you can see that the arrows indicate that that force is acting radially outwards. So we need to pick a direction. We're going to pick a direction. You can just pick any old edge in the model. I like to use the cardinal planes. And then we'll pick normal to plane. We're going to say a random number, 100 newtons. And now all the arrows go in one direction, and you can see that it's applying a load there. Now, not only is it applying a pushing force to the inside surface on this side, but when you do this, it's also going to apply a pulling force, like a suction, to the elements on this side. So you can't always get away with just applying a straight force. Sometimes you've got to use other boundary conditions like bearing load or something if you want to make sure that it's not putting a suction on this surface, which could be unrealistic. And let's just mesh it. So the mesh is basically how the computer divides the object into discrete grains that it can perform calculations on. And if we leave it at the default, this is what you get. Now, this seems fairly detailed at first. You got a lot of definition across the surface. You're like, do you really need that many elements? Seems like it might be too detailed. But we'll run it and we'll see what happens. Run this study. Okay, that ran in less than a second. And you can see that even though this part is, basically of a uniform cross section, you get a lot of noise down in here where this thing looks like it should be even, but as of course it's not. Same thing on this side. I'm going to change some of the options behind this stress plot to for convenience here. So let's see, I'm going to leave that at, let's go to megapascals. And then I'm going to go to my settings and I'm going to pick discrete just because it helps me a little bit more. So you can see, does that look correct? Probably not. We would expect that the peak stress would fall more or less uniformly along a continuous line here. And you really have no idea whether this is realistic or not because it only occurs at a single point. And it's very obvious that that is influenced by the coarseness of the mesh. And let's just take a note of this max stress here. So I'm going to click on this top value here. And you can see that it says 24.3784. I'm going to click on this annotation button right here. And that's going to show me where the max stress in this model is. And it says the max stress is 2.438, and it's at a single point. And we'll make a note of that. I'm going to go to Notepad. Actually, go to Excel. And we'll just call this default mesh entropy. Then stress. And we'll call this default. And how do I quantify that? Well, let's see. If I go to my create mesh option, oops. So if I look at this and we're creating a standard mesh and the global size is 2.2 and the tolerance is 0.11. And the stress reported is 2.438 E1. So that's 24 megapascals. Now let's try if we change that. Let's bump up the density. Let's, what does that give us? That gives us 1.6 and 0.08. And you can see now, whereas there was only one element across this curve, now there's two. So it's created a line of nodes in the middle of this 90-degree fillet. So we'll say 1.6, 0.08. And we'll run the study. And look immediately as to how much more uniform that stress plot looks, because the elements across that fillet are much more uniformly distributed, and they therefore give a much more uniform result. And here we get 2.554 e to the 1. Okay. And we'll do it one more time. We'll drag this all the way off to the right, make it super fine. And now there's 3 elements across that fillet. And we'll run it. Notice how it doesn't solve instantaneously. It actually takes a couple of seconds. And our max stress, this is a symmetric model. We'll say that the compressive stress on one side and the tensile stress on the other side are going to be about equal. So we'll just use the same number, even though it's on the other side of the fillet, 2.648. See, what were my mesh settings here? 1.13 and 0.056. Okay. And let's just compare these numbers. So we'll say that just put in a little line chart. So you can see the stress does go up. Let's set that to 0. Not by much, but it does go up. And we'll just look at the delta here. Let's see, D4 equals that minus that. To a percentage. So you can see that our stresses were 8% lower than what we predicted at the finest resolution when we used a coarse mesh. 8% doesn't necessarily sound like a lot, but when you're solving problems in aerospace in particular, and when you're doing fatigue problems, which you're not doing admittedly as students, but that's a big difference, and that'll eat up all your margin. So it's important to note that you really don't want to take advantage of the default mesh size in SolidWorks unless you know that that's going to give you accurate results in the areas that you're interested in. So let's take this a step further. Let's go really fine. So we've already dragged this slider off to the far right, and we're still using a standard mesh. Let's see if we drop this down to 0.05. We can just type in a value, and now it's like off the scale. If this was on the slider, it'd be off the scale. And notice how it takes a long time to mesh. Oh, you know what? I screwed up there. That should be 0.5, not 0.05. Okay, now we have 1, 2, 3, 4, 5, 6 elements across that fillet. And we'll run it. And it'll still solve reasonably quickly because this is just a simple static model. Pay attention to the number of nodes, number of elements, and degrees of freedom. 2 million is probably a good upper limit for what you want to try and solve in simple static problems like this, to have it solve in reasonable amounts of time. Okay, that looks really smooth, doesn't it? Okay, now you can see how much longer that took to solve than our first, our very first iteration that solved basically as soon as we click the button. Mesh density, as you decrease the element size, the mesh density goes up geometrically, and your solve times go up geometrically as well. So what's our max stress here? 2.724. One. So let's change that. Okay. So if we use our new result as the baseline, now we've kind of shown that we're only 3% away from the finest option available in the slider by default in Solidworks. Previously this was 8% with respect to the finest option. But if you go off the scale, you only go 3% beyond that, and you start getting into long solve times. Now, 3% is generally not going to be something you're going to care too much about. So we really didn't need to go that high in terms of mesh density. As it turns out, the rule of thumb is for fillets, you get the best results when you've got about 4 elements across a 90-degree arc. And we're going to use a trick. We're going to select an option that allows us to get that level of detail in the fillets without exploding the model everywhere else. You know, we don't need all these elements over here. They're not useful. We only care about the detail in here. So I'm going to go into my Create Mesh option again. And I'm going to select curvature-based mesh. And we're going to change the minimum number of elements in a circle to 16. This is a 90-degree arc. That's a quarter of a circle. We want 4 elements in a quarter of a circle. That's 16 elements in an entire circle. And this fillet has a radius of 2. Let's see. So what is that? So let's see if the radius is 2, and then the arc length is going to be, let's see, 2 times that times 2 to get the diameter times pi to get the circumference, and then divide by 4 to get the 90-degree arc. So it's an arc length of 3.14. So our element size needs to be going to be this divided by that. So our max element size is going to be about 0.78 millimeters. So right now it's set to 2.2. So we're just going to drop that down and we'll set it to 0.7. And this will update by itself correspondingly. And notice that this is also off the scale. In practice, I tend not to rely on this slider for what it's worth. We'll just hit OK. See what it did here? I screwed up. This mesh is every bit as fine as the normal one, and it's because I selected the wrong option. This should have been whatever it wants to be. And we'll set this one to 0.7. This is the minimum element size. We'll put this one back at 2.2, which is what it was before. Okay, there we go. So now we've got this coarse mesh everywhere else, but we have the level of detail in the fillet kind of that we want. It's not pretty, it's not super, organized and clean, but it's detailed. And we'll run this study. And it solves almost instantaneously. And our max stress is 2.776 E⁻². And we'll call this curvature. And the global size is 2.2, and this is a new set of options. .776. Okay, so we got results that are within 2% of the off-the-scale mesh density setting using a default or the standard quality level of mesh. So this curvature-based mesh option here is kind of the option that I default to with almost all of my models. It takes a little bit longer to mesh sometimes, but it's worth it because it doesn't waste modeling computation time on other areas of the model. You get all the detail you want in the fillets without all the overhead of trying to calculate wasteful detail in solid areas that don't need it. So we can take this and establish a rule of thumb. So the rule of thumb is 4 elements in 90-degree arc for acceptable accuracy in a fillet. And I'm gonna shift gears. So one of the other topics that was here to be discussed was design studies. So we're going to refine this discussion on mesh density with a design study. I have this static model here, and I'm going to create a new model. New study. And we're going to pick design study. You may or may not have access to this on an educational license, but it is worth going over. A design study is going to piggyback off of the results of another model that you've already run. So, static 1 or any of these others. And now we've got this new view down here. This is the design study window. And in it, you're going to choose the variables that you're going to change, the constraints that those variables have to follow, and the goals, that is to say the outputs of the model that you want to measure to determine the effect of changing the variables. So in this case, I've got no variables. I'm just going to I'm just going to click on this. I'm going to add a parameter. And I'm presented with an option here. So this is name, category could be a model dimension, global variable, simulation, material. So in this case, we're going to pick simulation because we're going to be changing something about the simulation that we ran. Drag this over here. I'm going to give this a name. I'm going to call this mesh entity, or actually we'll call this in circle. And we'll just start with 4. Actually, we'll start with 16. Apply. Okay, why is it? I'm a little rusty on this because I haven't done it in a while. I'm going to disable the optimization checkbox here. Now, usually this would have, let's see. Go back here. Item selection. Select the items from the simulation trees that you would like to link this parameter. Okay. So I'm going to, now that I'm in this window, I'm going to go back to the static model. Going to pick mesh. And then once I pick mesh, it pops up here. And then the list of parameters within the mesh option will populate, and I can pick the thing that I want to change. So in this case, I'm going to pick minimum number of elements, hit apply. And there's a little star that appears in the linked column here that shows that this is what this now refers to. OK. Now let's go back to the static one. And we'll create a mesh. And we're just going to notice that this parameter here is now grayed out. I can't change it. And that's because it's linked to the design study. And since we're going to be running an experiment where we change this to numbers that would create smaller and smaller elements, I'm going to set this really, really small, 0.05 millimeters. It's actually not going to get that small, but we're just setting a lower bound. We'll hit OK. We're going to go back to our design study, and we're going to see that our elements in circle, the minimum is 8, which would be 2 across a 90-degree fillet. And our max would be 24. Let's see, what's 24 divided by 4? That's 6. Let's set this really high. Let's set this to like, let's see, what's 8? So I want to do 1, 2, 3, 4, 5, 6, 7, 8, 32. Okay, and then our step is going to be an increment of 4 because a circle is 4 90-degree arcs. So every time we go up by 4, we're actually adding 1 element to the circle. Just hit enter. And I don't think I need to have any constraints, but I could be wrong. So we'll add a sensor. And it's going to give us this menu where we can add a sensor. A sensor is just something that measures something about your model. And you can add sensors in other ways. There's other ways to add sensors in the model tree, but I usually go through this. And we're going to pick simulation data. And the quantity that we're interested in is going to be stress. And we're interested in the von Mises stress. You can pick other values too. I'm going to pick megapascals. And we're going to pick the stress. Now we could pick model max because we know that the max stress for the entire model is one of these 2 fillets. But just to make sure that we're actually in these 2 fillets, I'm going to pick max over selected entities. And we'll just pick that one face. We could pick either face. You know, it is, you know, this is going to be the, you know, positive. This is going to be negative. But because it's von Mises, it's all absolute. We could pick both faces, but we'll just pick the one. Can leave this across all model steps. We're in a static simulation. There is only one step. Oops. And we'll just hit OK. So the constraints are going to be what the simulation measures when it runs. And right now it's being treated as a constraint, but we're going to select this option to say monitor only, because that's all we want to do. And we'll scroll down. And because this is not an optimization problem, we don't care about goals. We're just going to run a bunch of load cases in series, and it'll spit out the results, and we'll digest the outputs ourselves. At this point, I've created this. I don't want Solidworks to crash, but we'll save it. And we'll just run. And it's going to run through, and it runs the initial case, and then it runs scenario 1. So all of this creating a mesh and then solving the problem is happening in the background. So you could think, oh, it's going to take forever if you pick options that are too detailed on your high end. But you can hit stop at any point, and it'll finish its current calculation and then just you know, leave the others grayed out. Okay. So we can pick on a scenario, pick results and graphs, and stress is what we were measuring. So we'll double click on that. And it's going to show us the stress in the model. And let's see, why? Okay. And then we can pick different options. If I click here, that should update. Why is it not updating? Okay, so something's gone wrong here. First of all of these numbers look very similar. So I'm not sure what's up with this. Let's figure it out. I'm going to change my stress plot. And we're going to go to our chart options. Let's see. We're going to go to settings. And the boundary options will say the boundary can be the mesh. And we display that. Okay, so that'll show the mesh now. So we'll be able to see, hopefully. There we go. Okay, so when I click on this, we should see the mesh changing. And yet it's not. So I must have set something wrong in the variable view. So we've selected range with steps. Okay, elements in circle. Double click on that. Oh, just okay. Value, max element size, min element size, mesh and static 1. So that should be linked. Okay, what did I do wrong here? Did I miss an option here? No. Well, let's see what happens if I change this to discrete values. So we'll set this to 8, 12, 16, 32, no, 16, 20. Still give me the same results. So what did I do wrong? Wonder if it's got to do with this. No, this is in millimeters. Okay.
I have a question.
Yeah.
So you've got that value 20, which is referring to the number of elements across that arc. How exactly have you linked that number to the min and max element values? Like
it's not linked to. Oh, sorry.
like, yeah, how are those linked together so that it's accurately increasing or decreasing the size of the elements to match that number?
So what's supposed to happen is the maximum element size is going to be the maximum element size across the model. So all these little triangles that it creates across the model, the biggest one that it's going to create is going to be 2.2 millimeters across. And the smallest one that it's going to create, if it wants to, the smallest possible one that it's going to create is going to be right now 0.01. But it's only going to do that if it feels a need to, based on the number of elements in a circle that I've told it to.
So that parameter is like SolidWorks is actually interpreting that as the min elements in a circle.
20, yeah, so the minimum number of elements in a circle is going to be 20.
Okay, so you haven't done that with a formula, like that's an option in SolidWorks to say?
That's, so when you pick curvature-based mesh as opposed to standard, so if I go back to standard mesh,
okay,
so that option goes away. When you pick curvature-based mesh,
oh, I see.
that's where you get that option.
Okay, so yeah, it actually is built into the software.
Yeah.
Okay.
Yeah.
That makes sense.
So this should give me 5 elements across that arc. When you use curvature-based mesh, you can set the minimum element size to be pretty small. So this is, it seems about right. Yeah, see, I can't change it in the design study now. So if I delete this, whoops. Okay, what did I do here? Okay. Delete. So if I delete that parameter and I go back to the static model and we create a mesh, let's just make sure that it reacts the way we want it to when we set options manually. Okay, so let's set this to say 32. So that's going to give us 16 elements across this fillet. Okay, there we go. So why is it not giving us 16 actual elements? 1, 2, 3, 4, 5, 6, 7, 8. Oh, sorry, 8. Yeah, that is 32 divided by 4. Okay. So probe. So let's look at this element. So this element is 2.58. Oh, that's not even giving me the, yeah. Okay, let's see if the setting the minimum size to some super low number had the effect that I wanted. So we'll go back to the design study. Go back to the elements circle. Cancel. That's interesting. So it's no longer visible in here. So I deleted it, and now it's a ghost parameter that doesn't control anything, and I can't change it. SolidWorks can be really buggy like that. So I'll just delete that. I'll create a new variable. I'll just call it each circle, elements in circle. And we'll change this to simulation. Go to our static tab. We'll pick our mesh. Pick our minimum number of elements. Apply. Oh, got to enter a value. So we'll call that 8. Hit apply. Now it's linked. Okay, and we're back in our design study. Min, let's see, min of 8, max of 32, steps of 4, enter, save. This works a lot better when you're changing dimensions. Like you can, instead of changing parameters for your mesher, you can actually tell it to change dimensions in your model, and that's really where it's most useful. So I might do that next if this doesn't work out the way I'm expecting it to.
Are the elements in the mesh tetrahedrons, or are they just two-dimensional, like across the surface of the model?
They are tetrahedrons. And in fact, if you look into this a little bit further, they are tetrahedrons with mid-side nodes. So they're not perfect tetrahedrons. They actually capture the curvature via having a node in the middle of each edge. It does enable the model to be more accurate for the same number of tetrahedrons, and it does solve faster. Okay. Kind of surprised that this is taking as long as it is. I wouldn't expect it to, I would expect that it should be able to blast through the first couple of models, and yet it's not. So can any of you guys confirm that you have access to design studies in the educational license?
I believe we do. We also have access to frequency analysis as well, and some of the basic flow simulation.
Okay. So it's not giving me the results that I want. So notice how it's displaying basically the same answer for all of these options. The reason it's displaying the same answer is because it's trying to solve the problem with the same mesh. If it changed the mesh in any way, you would show a different answer. I wonder if it's the fact that optimization is not selected. I think it could be that there's a option or something within SolidWorks where if this is checked or not checked, it may optimize certain things in the background to reduce the workload for the computer, and it may not decide to update the mesh even when it should. I don't know. We're coming up on time for the first hour, so let's take a 10-minute break. I will continue to play with this to see if I can figure it out. You know, go get a drink or do whatever you guys want to do in the meantime. Yeah.
All right.
So we're recording?
Yeah.
Okay. So just so that make sure that it's captured on the recording, it looks like the issue was a bug within SolidWorks.
You're not sharing your screen.
Yeah, I'm not sharing my screen yet. I'm going to start in just yeah. Let's see. Clip to the max. Okay, so let's see. Start. Share my screen. Okay, am I sharing my SolidWorks screen or my presentation screen?
The SolidWorks.
Okay. So yeah, so it looks like it was a bug. Oops. So the trick, let me just delete this. Okay. So I was changing options within the master mesh. So this is the master mesh control panel. And apparently SolidWorks didn't like that. So I tried it with a mesh control. So a mesh control is something that you can apply as a local refinement on the mesh. So you can declare different meshing options for specific faces. So we're going to do it this way instead. So I'm going to select this face, and I'm going to manually declare that I want a 0.7, we'll say, mesh size on that face, and ignore ratio. So the ratio is forget what that is. It's you can look it up later, but we'll just hit OK. And now when SolidWorks creates a mesh, it's going to create all the other faces consistent with the master rule, and then this one face, it's going to try to implement the rules that you gave it specific to that face. So we create mesh. Okay, and now notice how this face is different than this face. So this face is meshed using the master control. And this face, we explicitly declared using this mesh control to have elements of a certain size. So I'm going to go back to our design study, and I'm going to optimize the mesh density this way. So I know that the arc length for that fillet right there is 3.14 millimeters. And so if I want to have one element across that arc, my element size is going to be 3.14. If I want two elements across the arc, it's going to be 1.57, blah, blah, blah. So you just divide the arc length by the number of elements that you want. And so I'm going to take these values, and I have a second screen, so I'm just going to drag this off to my other screen. And I'll go back to my design study, and we're going to change our variables. I'm going to add a parameter. I'm going to call this element size. And this is going to be simulation data. And we're going to go to the static tab, and we're going to select, instead of the master mesh, we're going to pick the control. And now it populates these two options, ratio and mesh size. And we want to change the mesh size, which is going to apply just to that face. I'm going to hit apply or OK. And it says, please enter a number. OK, so let's enter in a number. Say 1.57. Apply. OK. So now we get kicked back into the main design study tab. And we can't use range with steps anymore because our steps are, they follow an inverse curve. So we're just going to pick discrete values. Ooh, why does it say 1.57 meters? I wonder if that's what the issue was. So we're going to say 1.57 millimeters, and then 1.05 millimeters, and 0.79 millimeters, and 0.63 millimeters, 0.52, 0.45, and 0.39 millimeters. Enter. And you can see that's just the list here. I just typed out this list. So that'll give us between 1 to 8 elements in that arc. Going to give this a quick save. And we'll run it. And it's done. So we have our list of scenarios. And we can actually just take this, Control, copy, Control C. And I think we should just be able to paste that straight into Excel, just like that. Although, I hate how it comes in formatted like that. So if I cut and then paste special, let's see, copy, paste special, transpose, okay. So this is our element size. And this is our number of elements in arc. And that's going to be 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. Oh, sorry, started wrong. 2, 3, 4, 5, 6, 7, 8. Okay. This is our stress. And I'm going to select these, and I'm going to do Control H. Do a find and replace. I'm going to find space, Newton, millimeter squared, and I'm going to replace it with nothing. Replace all. Oh. There we go. And that'll just get rid of all the text that was part of that. And now we've got a list of the elements, the element size and the stress that it was produced. I'm going to go to Insert, and we'll make a little scatter plot here. And you can see that as the element size starts off small, your stresses shown in that fillet rise, and they rise, and eventually they hit kind of a stable point. When you get past 4 elements in that circle, you can see that the stress really doesn't change a whole lot. So the more detail you add to that mesh, you're not really gaining anything. And this plot kind of shows that 4 is the rule of thumb here. 4 elements in a 90-degree arc for acceptable accuracy in fillets. Any questions on this so far? No? Nobody? Can anyone hear me?
Yep, we still hear you.
Okay, very good. All right, so I just basically used a design study to show how the rule of thumb for element density applies to fillets. Let's go back and look at how that rule applies to solid objects. So let's go back to the static study, and I'm gonna suppress that. And let's see if we can get this to run on the master mesh. So I'm going to go back to create mesh, and I'm going to go back to a standard mesh, and we'll see what this shows. So that creates this nice uniform mesh. And notice that there's 4 elements through the thickness of this bar. And if I drag my mesh density all the way over to coarse, what does it give me? I can get 2 elements through that bar. But what I really want to get is 1 element through that bar. So let's set that to 10 millimeters because that bar is 10 millimeters in size. Okay, there we go. So this is going to be a super coarse mesh. Now, if you're trying to model a frame for a robot or something, and you've got a really complicated, piece of geometry, you might end up in situations like this. Probably not, but it's possible. And we're going to go back to the design study, and we'll see if we can get this to work this time. I don't know. I don't know why it would, because it didn't before, but we'll see. Suppress that, and we're going to call this add parameter global size, and this is going to be simulation, and we're going to go over to the static tab, and we're going to pick, so in static, click mesh, global size. That's why I had meters selected up here. Now it's selected millimeters. So this is 10 millimeters to start. Apply. Now it's linked. Okay. And we're going to do discrete values. So if we want 1 element through the thickness of this solid object, we get 10 millimeter element size. And notice how this is grayed out. So this is no longer going to be part of our design study. If I want 2 elements through the thickness of that, it's going to be a 5 millimeter element size. If I want 3, it's going to be 3.33. If I want 4, it's going to be 2.5. If I want 5, it's going to be 2 millimeters. And let's see, what is 10 divided by 6? 1.6. And 10 divided by 7, 1.42. And 10 divided by 8 is 1.25. Okay. And we'll run that. Maybe it'll work, maybe it won't. Okay, so for whatever reason, it seemed like it worked. Notice we're still getting the stress in this face. What I really wanted to do was add a measurement to measure the deflection in this bar, but we can see, there we go. So in the first case, it gives me a very coarse mesh. Actually, so this is an extremely coarse mesh with one element across the thickness, 2 elements across the thickness, 4 elements across the thickness. So I'm going to actually change my constraint. I'm going to change this. Whoops, delete. Add sensor. So I'm going to add a sensor, and this is going to be simulation data. I'm going to measure displacement. I'm going to measure displacement in the X direction. Actually, let's just measure resultant. That way it doesn't make me pick a coordinate system. Measure resultant displacement in millimeters, model max. Nope, we want max over selected entities. And we're going to pick the displacement at the face where we applied the boundary condition. Just hit OK. Make that monitor only. Unfortunately, I think I got to rerun it. Yeah, I got to rerun it, because it only stores the values that you tell it to store. Okay, so if I go to my results, here's my stress plot, and here's my displacement plot. And it's a, it's a cantilever beam, so it's going to displace the way a cantilever beam does. And we can see that if I take this and copy it over, we're going to open up a new tab, paste that, copy it again, paste special transpose, delete that. So this is going to be element size, and this is going to be elements across solid wall. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. Stress and displacement at tip. Do Control H, do a find and replace. We're going to find Newton per millimeter squared, replace with nothing. Okay. And we're going to do another find and replace. Control H, replace millimeters with nothing. And let's look at the displacement at the tip as it maps to the element size. So again, you can see that when you have a very coarse mesh, your displacement is not the same as when you pick a finer mesh. And that's because if you go back to your beam bending courses that you may have taken as a first or second year, you may remember that in a beam, you've got tension on one side of the beam, and you've got compression on the other side of the beam. And when you have a solid finite element, the computer doesn't really consider bending of a solid element very well. So if you've only got one element through the thickness, it can't consider tension on one side of that element and compression on the other side as accurately as if you've got elements that are experiencing specifically tension and elements that are experiencing specifically compression. So as you can see, once you hit, 4 or 5 elements through the thickness of the part, your displacement starts to converge to a limited amount. What this plot shows you is that after about 5 elements through the thickness of the part, you're not getting any more accuracy than you would with a super high detail fine mesh. All you're getting is longer and longer solve times. I can pull that over and let's look at what the effect is on stress there. So we can see that stress really isn't affected quite as much because really the stress in the fillet cares more about the number of elements at that fillet. But the displacement at the tip is affected. So the rule of thumb that I was always taught was actually 3 elements through the thickness. But we can see from this optimization study or this design study that may not necessarily be the case, that you might actually want to go to 5. So if I go to static, go to results, displacement, edit definition, settings, fringe, discrete, boundary options, mesh, hit OK. Hopefully that should be reflected in the design study. There we go. OK, so I double click on it. So if I go to scenario 5, we can see roughly what that looks like. So your most accurately modeled part is going to be a combination of the right number of elements through the thickness of the part and the right number of elements through the thickness of any particular solid object. So we'll go back to the static model and we'll go back to the mesh. And this is suppressed. Let's see, go to create mesh. And let's apply the rules that we just learned from our design study into accurately modeling this part. So we're going to pick curvature-based mesh. We're going to set the maximum element size to give us 5 elements through this thickness. This is a 10 millimeter thick part. We want 5 elements through the thickness, so our maximum size is going to be 2 millimeters. We want 4 elements through every radius on the part. And when we set this globally, it's going to apply this rule to all the different curved surfaces in the model. So we'll set this to 16. And with our minimum element size, will that give us 4 elements through this thickness? And I think the answer was, let's see, we need, for 4 elements in the arc, we need a minimum element size of 0.79. And our minimum here is less than that, so we're good. Create the mesh. And now we've got 1, 2, 3, 4 elements across this radius. And it's ugly, but we've got at least 5 across the thickness of this part. And we'll just run that. And this is a model where we can actually trust the results. So if we wanted to know how much this part deflected, we would get accurate results, assuming that the loads applied were right and that you actually knew that this was getting the right amount of force. But if this is true, if you are applying 100 newtons in this direction exactly, then we could generally trust that you're going to see 27 megapascals in the fillet, and you're going to see 1.1, so 0.01 millimeters of movement in the end of that bar. So what happens when you've got a model that you cut on the water jet, for example, say you're designing your part and you don't have a fillet there? Let's suppress that. Now you got a sharp corner. Let's go back to this design study. Oh, shoot. Sorry, I'm going to go back to my mesh. I'm going to create a mesh. I'm going to make sure that I've got standard mesh selected. And this will go back to having the linked parameter for the design study. So I've got standard mesh selected. Let's go back to the design study. Now, this stress constraint is no longer going to work because the fillet that it was measuring no longer exists. So we'll go to add sensor. We'll get into, oh, sorry. Let's see. Let's delete that. Let's add a sensor. And we're going to measure the simulation data, von Mises stress, megapascals, max over selected entities, and we're going to measure it right in that corner. Okay. This is something that you may be able to resolve more, that you may find you end up having to resolve with hand calculations, because what's going to happen here is as we increase the mesh size, or as we refine the mesh size, because this is a sharp corner, it's a perfect 90-degree angle. And actually, this is true for any sharp angle in any model that you run. But as you increase the mesh size on a sharp angle, the stress that is calculated in the FEA is going to diverge. It will never settle to a consistent value. So if you notice here, the stress is settled to a consistent value, about 27.5 megapascals. We're going to rerun this mesh study with a global size. Okay. And we'll look at the results. Stress. Okay. So the max stress here, let's see, which case is this? This is, oh, so this plot is showing the stress on this element. It's not showing the stress along the line that we chose. So we'll just take this data here, copy it into Excel, Control C, new sheet. Actually, let's go back to, let's do it on this one. No, we'll do it on a new sheet. Paste, copy, a special, transpose. Okay. Delete that. Stress. Displacement. Stress. Place all. Okay. Close. Control H. Find space, Newton, millimeter squared, replace with nothing, replace all. Okay. So what does it look like is happening with the displacement in the tip of that bracket? It's not really changing a whole lot. But the stress is. So let's do, let's say 1, 2, 3, 4, 5, 6, 7, 8. Number of elements. We will insert a scatter plot, and we can see it never actually reaches a flat spot. You can increase the number of elements to 1,000, and the stress in that corner will shoot off to infinity. So how do you know whether you're actually getting accurate results from this model? And the answer is you don't. You cannot trust simulation results at sharp corners. You never know if your mesh size is going to reflect the actual stress. So what the usual thing to do is to always have a fillet in all your corners. Oops. And you can make it small. So if you, for example, if you know that the water jet cutter has a kerf of, say, 0.5 millimeter, so you put in the fillet that the water jet cutter actually has, and you run your models with that fillet size. And that'll give you a smooth transition, and you can actually use mesh controls to influence the mesh density of that specific fillet without really dragging down the rest of your model, making it super high detail. The other alternative is to just ignore the stress results that happen in those sharp corners. You can say, well, I don't necessarily know that that's going to be a failure point in the model. So if I want to know, if I'm trying to simulate the whole frame of my robot, in order to make it easier, I'm going to just look at the stress results, and the computer is going to tell me, oh, I got a peak stress right here in the sharp corner. And you're just going to ignore that, and you're going to use the probe tool. We'll just run this study real quick. Okay. So, it's like, obviously the stresses went up because I increased, or I made this into a super small fillet. But you could say, maybe I'm not interested in the stresses here. Maybe I'm interested in the stresses somewhere else in the model. So we will just use the probe tool, and we will manually get the stresses at some other point. Say I was interested in the stresses down here near the boundary condition. I'll just probe that, and I'll forget this because that's not what I'm interested in. So. Any other questions so far? No questions? Okay. Let's change this design study. Let's look at how this design study could be used to help you design the robot or design whatever project you're working on at the time. I have a bracket, I've got fillets. I want to figure out how big my bracket needs to be. Going to, let's see. Cancel. Okay, I'm gonna make a new design study. Create a new design study. I'm gonna add a parameter. And this time we're gonna change a model dimension. So we're gonna add a model dimension. We're gonna call this bracket length. And this will be a model dimension. And we will choose sketch 1, and it's already popped up. I guess it's because sometimes it doesn't do that, but we can just pick a dimension here on the part, and we'll say 35. We'll pick this dimension, this 35 millimeter length, and we'll choose bracket height, and the bracket height we're going to pick that dimension, and you see the little link pops up. And we're going to choose fillet radius. And we're going to pick that dimension. That's going to be our 1/4 millimeter fillet, and that's linked. Okay. So we're going to add variables. So bracket length was already there. So we're going to have bracket height, and we're going to add fillet radius. And our constraints, we're going to pick stress 1, which is the stress in that fillet. And we're going to pick monitor only. And now we've got the optimization checkbox checked. And with that checkbox checked, that enables us to use the goals tab. And under goals, we can pick, that's interesting. Delete, that's why. We're going to go back and we're going to use the stress in that fillet as the goal. And we're going to say we want to minimize the stress in that fillet. And just to make sure that it's meshing correctly, we're going to go back to our design, our static model. Going to suppress that, going to create mesh. I'm going to make sure that I'm using a curvature-based mesh with element size of 2. That'll give me 5 elements through the thickness of the model. And let's see, let's just use that, say 0.4 millimeters. Okay. So that would give me 6 elements in an arc for a 1 millimeter radius fillet. So we'll go to our design study. And we're going to let our fillet radius be a minimum of 1, a maximum of, say, 3. And we're going to let our steps be 1 millimeter. So it's going to simulate 1 millimeter, 2 millimeter, and 3 millimeter fillet radius. We're going to choose discrete values for the bracket height. We could have 35 millimeters, or we could have, say, 70 millimeters. And the bracket length, we could choose 35. Discrete values. And 70 and now it says, how many scenarios do we have? It says we have 6. Is that right? That doesn't seem right. That should be 1, 2, 3. That should be 4. 2 options times 2 options. That should be 4. And then 3 options here. That should give us 12. So what's wrong here? Go to add parameter. Bracket length is dimension D10. Bracket height is dimension D9. Fillet radius is dimension D1. Okay. What happens if I just do discrete values? Let's do 1, 2, 3. It may not be updating this correctly. We'll run it. We'll see what happens. Yeah, okay. So it says we've got 14 scenarios. That's because it has 12 actual scenarios to model, plus an initial and an optimal. And you can see it's updating the model in the background. And because we went through the work to determine what the optimal mesh size rules are, we know that the results between these different models are going to be useful and comparable. You could, if you didn't know the rules for mesh density, create a design study where you have different dimensions on your parts, but the number of elements across the fillet could be different as you shrink and grow the fillet. And you could be getting inaccurate results for small fillets that may make them look better or worse than larger fillets. Okay, so what is this saying? So it says the initial load case that we started with was 35, 35, and 0.25 millimeters. So this is the basic design that I had before entering any parameters in. So this ignores the parameters that I put in for that dimension. And then all of these scenarios are going to be the parameters that I actually told it to run. So 1, 2, and 3. And it's going to tell you that the optimal is design option number 9, scenario number 9, which is 35 millimeter lengths on the 2 arms and a 3 millimeter fillet. Does that surprise you? It should not, because when you've got shorter lever arms, you have lower stress. And when you have larger fillets, you have lower stress. And what is our worst case? Looks like, let's see, scenario 4 is probably going to be the worst. That's got the longest arms and it's got the smallest fillet. So we go from 76 megapascals of stress in that fillet down to 22.6. And that was enabled by the use of the design study that allows you to tell the computer, hey, cycle through all these options, don't make me, iterate through them. You can do this for things like pretty much any dimension in the model that you care to. It's not the same as topology optimization, which maybe you guys have heard of generative design, which makes these really crazy organic shapes. This is optimization at a much more basic level. But when you're doing traditional manufacturing methods, this is what you're going to use. Any other questions?
That's really cool. This will work for basically anything you smart dimension. So like you could do it for like a diameter or like an internal radius, for example.
Yeah. So let's get an example of what happens when it fails.
Okay.
So
yeah,
I'm gonna add another parameter. So I'm gonna add a hole size parameter, and I'm gonna pick a model dimension. And let's pick this parameter right here, this 4 millimeter hole where my loads are created. And it's automatically linked, and we'll hit OK. I'm going to suppress that, suppress that, suppress that. You could delete it too. And if my hole starts at 4 millimeters, if I make this say 8 millimeters, it's still within the size of the bracket. But if I go to say 12 millimeters, that hole is actually going to be larger than the bracket, and the sketch, the extrusion is going to fail. So let's see what happens when we do that. Okay, that's interesting. So the extrusion didn't fail. So Solidworks is actually smart enough to extrude, to chop off the top of that extrusion. It didn't used to be that smart. So you can see that I've got the sketch highlighted. And in other older versions of Solidworks, it would extrude and you'd get these two chunks, or it wouldn't know what to do with this circle. But what'll happen is you'll get it'll show like it'll just say that this update failed, and it'll run the ones that actually worked, and all the ones that failed, it'll just say it failed. So. Yeah. Okay. So one point about the parameters that get linked into your models here. All of these parameters, if I go to the variable view, bracket length, bracket height, fillet radius, these are now controlled by the design study. If I go back to my model, I can change this, right? That's not a big deal. So just make it 4 millimeters and it goes back. But for stuff like, if I go to my static model where my mesh size is controlled by a parameter. So you got to create mesh. The mesh size is highlighted. Oh, let's see if I go to standard mesh. Okay. So notice how under the standard mesh option, the global element size is grayed out. I can't change it because that's part of the design study. Say I want to go dick with it. I have to go delete it from the design. I could delete it from the design study, but it would still be, this value would still be linked to a parameter that's kind of stored, deep in the bowels of SolidWorks. And there's ways to get access to that parameter, without, once you've accidentally deleted it from the design study. But what we're going to do here is we're going to click on this tab here, and we're going to just go to unlink value. You can unlink it. And now it's no longer associated to the value that's in the design study. And if I click on that again, I can link it. And now it's going to ask me to link it to a parameter. And I can, either link it to an existing parameter that I've defined, or I can do edit define, and it takes me back to the parameters list, and I can make a new parameter for it, or I can link it back to, say, that parameter which it was linked to before. So now it's grayed out because it's linked to a SolidWorks parameter. I'll unlink it, link it again, go back to global size. Okay, so if I go to design study, oh, it's going to create the mesh, darn it. Okay. So if I go to my design study and suppress that, so let's delete this. Oh, why did I do that? Oh, wrong one. Okay, so I delete this. What? Okay, it was supposed to give me an error message. It was supposed to say, are you sure you want to delete this because it's linked to a parameter? And what will happen is, what could happen is you could create this as a variable, like global size, and then you delete this and it says, are you sure you want to delete it because it's linked? And then you go back to your static model, your original FEA model, and you go to edit your mesh, and you can't change this anymore because it's linked to a parameter that you thought you no longer have access to, or you want to be able to change it. So the solution to that is just unlink it, and then you can go back and edit it manually. So that's all. That was my only point.